Okay, good afternoon. Welcome back. And I think it's time for us to resume the program, the afternoon program. And the next speaker is Professor Chiung Hwang from University of Science and Technology of China. And he's gonna, I guess, revisit the maximally supersymmetric super Yang-Mills theory in 3 dimensions. Yeah, please.
Thank you. Thank you for the introduction. And first of all, I'd like to say I'm very happy to be back in Seoul and at KIAS. And I really appreciate the invitation and this opportunity to talk about my ongoing work about this maximally supersymmetric Yang-Mills theory in 3 dimensions, which is done with wonderful collaborators Riccardo Gomi, Simone Giacomelli, Fabio Marino, and Matteo Sacchi. So there is a famous story written by Mark Twain, a story about 2 boys who have very similar looking, but completely different lives. One as a prince, and the other as a pauper. I guess most of you know this story. The thing is that I found that there is a similar story. Okay, so something's wrong here. There's a similar story in physics for the maximal supersymmetric Yang-Mills theory and 3D maximally supersymmetric Yang-Mills theory. So as you know, this 4D maximal supersymmetric Yang-Mills theory, n equal to 4 super Yang-Mills theory, is one of the most appreciated examples in high-energy physics. So someone says it's like a harmonic oscillator in 21st century. So as we know, it exhibits many interesting properties like exact superconformal symmetry and S-duality, also like ADS-CFT correspondence. On the other hand, if you just check the literature, you never see any deep discussion of this 3D n equal to A super Yang-Mills, although it has exactly the same matter contents as the 4D maximum supersymmetric, 4D n equal to 4 super Yang-Mills. Why is that? I'm going to tell you the reason shortly, but due to this reason, so which is basically due to the strong coupling effect, people never discuss the details or details of IR dynamics of this 3D n equal to A super Yang-Mills in the literature. So in this talk, I'm going to show you how we can overcome this difficulty and what we can learn about this IR dynamics of 3D n equal to 4 super Yang-Mills. Okay, so let me first briefly recall what we know about 3D n equal to A super Yang-Mills. So it is a 3-dimensional super Yang-Mills theory with the 3 adjoint chiral, which is exactly the same as 4D maximum n equal to 4 super Yang-Mills. And it is the world volume theory of D2 branes, which becomes M2 branes in strong coupling limit. And like any other 3D gauge theory does, it becomes strongly coupled in the IR. And due to this fact, it is hard to analyze this theory in a standard perturbative way. So in that case, we usually adopt the study of these protected observables, like supersymmetric partition functions, which are independent of the RG flow. The thing is that even this approach is not very useful in this case. Why is that? So it turns out the correct IR symmetry, especially the R symmetry of this n equal to n equal to A super Yang-Mills is different from UV symmetry. And we are only able to access this UV data. And due to this reason, people usually use other theory descriptions like ABJM or the n equal to 4 SQCD with one adjoint hyper and one fundamental hyper, which is called the ADHN quiver. And indeed, using those descriptions, we have studied this n equal to A superconformal field theory in 3D, like black hole entropy and other many interesting properties, but not this 3D n equal to A super Yang-Mills directly, which is completely different story from 4D case, right? So I want to emphasize that in this talk, I'm not going to tell you about the property of this n equal to A superconformal field theory because we already know well. So instead, I will tell you this n equal to A super Yang-Mills, which is believed to flow to this n equal to A superconformal field theory. It actually has much more non-trivial structure in IR in the IR in the low energy. Okay. And the thing is that the issue of this maximal super Yang-Mills theorem, n equal to A Yang-Mills theory, is not only for this theory. It appears more generally. So in general, this theory belongs to a class of 3D gauge theories called bad, according to this Guyot-Witten's classification. And this bad theory includes the monopole operators, which decouple in the IR, whose naive conformal dimensions are less than 1/2, and typically even even negative. In such a case, we know that due to this unitarity restriction, it violates the unitarity of the theory. So in order to have consistent unitary CFT in the IR, there must be emergent symmetries arising in the IR which correct R symmetry, such that we have a consistent R symmetry charge. And as I tell you in the previous slide, the superconformal IR symmetry of bad theory is different from the manifest UVR symmetry. The thing is that, well, why this is bad? The thing is that if we try to compute like a supersymmetric partition function, like a squashed three sphere or superconformal index, in that case, those partition functions are divergent if we have a negative R charge. Because if you examine the asymptotic behavior of the integrand, for example, then it scales like this, where this R of M is the R charge of monopole operator, and this is X is the integration variable. So in the asymptotic region, the integrand diverges. So naively, the partition function diverges in such a case. Nevertheless, one might ask, okay, it's fine because we don't have a correct access to the correct IR symmetry. It is okay, partition function may be divergent. But the thing is that even in such a case, whether we can extract some useful or meaningful information out of this. And the answer turns out to be yes, if we use something called mirror dualization algorithm. Okay. Okay. So here's the outline. So I'm going to tell you what this mirror dualization algorithm is. And this is something about the 3D mirror symmetry, which I will explain the details shortly. And I will show you two examples, good SQCD and bad SQCD, to demonstrate the difference between those two theories from the perspective of this algorithm. And then I move on to the application to the circular quivers. And it turns out, unlike this SQCD case, this circular quiver has much more complicated structure regarding this badness of theory. So indeed, there are two types of badness of this gauge theory, which I call the locally bad and globally bad. And I will explain each case using some examples. And at the end, so we will encounter this 3D n equal to A super Yang-Mills as an example of these globally bad circular quivers. Good. So let me explain what this is. So this mirror dualization algorithm is about 3D mirror symmetry, which is an IR duality, typically relating two 3D n equal to 4 theories whose Higgs and Coulomb branches are exchanged. And it has a deep connection to the S element of this as a 2G symmetry of type 2B string theory, as we know, which exchange the NS5 and D5 branes. The mirror dualization algorithm is an algorithmic and field theoretic framework for constructing the 3D mirror symmetry from two fundamental building blocks. So it is related to string theory, but so our previous understanding of 3D mirror mostly relies on the connection with the string theory. On the other hand, here I try to convince you that we can understand this 3D mirror symmetry purely from the field theory perspective. Okay, so what I mean by the fundamental building blocks of 3D mirror symmetry. So the core idea is that instead of dualizing the entire theory, I try to dualize each field in a certain representation. So in this case, I will consider the bifundamental field and fundamental field, and I try to dualize them. Okay, so if I dualize this bifundamental field, it is due to this rather complicated 3D quiver gauge theory. Okay, maybe I should explain the notation first. So this square node is some global symmetry, UN global symmetry, and this circular node is a gauge symmetry. And the edge connecting those two nodes correspond to the field in a hypermultiply in the bifundamental representation. And this U denote the Fy parameter associated with this UN, in this case, global symmetry, and X and Y are the mass parameters or some symmetry fugacities associated with this UN global symmetry. Okay, and I claim that, okay, this is due to this theory. So this is a free bifundamental, and this is interacting gauge theory. And you might wonder, on the left-hand side, we have two UN global symmetries, but on the right-hand side, we don't. So the origin of this UN global symmetry from the right-hand side is the following fact. So if you look at this theory carefully, then you can notice that this part is nothing but something called TUN theory, which is defined in this way. So it is a linear quiver gauge theory with a U1, U2, and so on up to UN minus 1. And there are n flavors attached to that last gauge node. And this is a TUN theory. So I construct the theory on the right-hand side by gauging one single flavor together with the two TUN tails. Okay? The well-known fact about this TUN theory is that in 3D, we have some global symmetry associated with each UN gauge node, which we usually call the topological symmetry. So if you look at this part, we have U1 to the n global symmetry. But in the IR, it is known that this symmetry is enhanced to UN symmetry. Okay, so on the left-hand side, we have a manifest flavor symmetry, flavor UN symmetry. On the right-hand side, we have emergent UN symmetries in the IR, and they are mapped. Okay, but from this diagram, it is not clear whether we have this one. So instead, I'm going to use this shorthand notation. So this part just denotes the same TUN theory, but I just present the enhanced UN symmetry explicitly. Okay, so this square node, which corresponds to some global UN symmetry, actually means the UN symmetry which only exists in the IR. Okay, so yeah, so this bifundamental is due to single fundamental field sandwiched between the two TUN tails. And there is another relation, which is actually the inverse relation of this one. So now I want to dualize this fundamental field. And then it becomes bifundamental sandwiched between the same TUN tails. Okay? Yes, please.
The original context of mirror symmetry, there's no field theory proof of this. You just have, brain construction.
Yes, of course. Yes, that's true.
So what's the argument for this?
A very good question. So let me answer in two steps. So our original motivation was also inspired by string theory. We just interpret all the brain move in string theory in terms of field theory ingredient, like field and stuff. And it turns out this bifundamental, you can understand this bifundamental as just excitation between the D5 brain attached to NS5. And you can also understand this fundamental as a so fundamental field as an excitation between the, previously, so this is the excitation on the D3 brain attached to the D5, NS5. In this case, it is the excitation of D3 attached to the D5 brain, right? And then the role of this TUN is just a local S dualization from the field theory perspective. So I just locally dualized NS5 into D5 and D5 into NS5. Then the question is, okay, so that is motivation. Then how do we know whether this is correct at the field theory level? We can prove this duality assuming some other duality, well-known duality in 3D, which is Aaroni duality. So we just derive this, duality, just iteratively apply this Aaroni duality on each gauge node. So if we believe Aaroni duality is true, then this should be true. Okay, so there is another duality relation. And you can see this delta, and I should explain what it means. So because on the right-hand side, we have two UN global symmetries, but on the left-hand side, we only have a single one with an extra delta. So this is actually another theory identifying those two UN symmetries. So it is kind of, okay, let me explain the next slide. Okay, let's consider this TUN theory glued together, but now without the fundamental field. So previously we considered the two TUN tail with a single fundamental field, but now I just consider the two TUN glued together, which looks like this, okay? And this TUN theory have some moduli space parameterized by its monopole operators, which charged on the enhanced topological UN squared symmetry, as I mentioned. So there are two UN symmetries, and in this case, they should be realized as an enhanced topological symmetry. The thing is that we can compute the partition function of this theory, and we found that the partition function is exactly delta between x and y, the two mass parameters. What does it mean? It means that the moduli space should be smooth, such that this UN times UN symmetry must be spontaneously broken on the point of the moduli space. Okay, so this delta encodes the fact that this theory has a smooth moduli space with non-zero BEV at every point. Okay, and here I mentioned that okay, I combine two TUN by gauging the common flavor symmetry, but we can also gauge the topological symmetry instead of the flavor symmetry. In that case, just their roles are swapped. So you can either gauge the flavor symmetry to construct this theory, or some other theory where you gauge the enhanced topological symmetry of the two TUN tails, which is non-Lagrangian, of course, because you gauge the emergent symmetry, but the relations still hold. Okay, the partition function of that theory is also proportional to delta, and we expect that the moduli space should be smooth, okay? Then in the previous slide, what this really means is that here we have another quiver gauge theory, which triggers the RG flow such that in the IR, the putative two symmetry, UN symmetries are spontaneously broken to the diagonal one, okay? Anyway, so we have those two blocks, which will be used as the building blocks of 3D mirror symmetry. I will show you the example later. But before moving into the example, I'd like to introduce a slight deformation of this building block. So I show you this is a TUN tail, but now I want to break this flavor symmetry slightly by either turning on the nilpotent mass term or monopole potential, okay? Because we have topological symmetry and flavor symmetry, so we can either break one of those two, okay? And then the UN symmetry can be broken into the sum m um times u1, where this m is smaller than this n, okay? And we denote this deformed theory in this way. So why do we need this? The thing is that once we use this deformed S-duality, deformed TUN theory, we can actually find that we can generalize the previous duality relation slightly, such that now we can consider the bifundamental field between the unequal ranks. So in the previous slide, what I show you is the dualization of the bifundamental with the equal ranks. But if I use this deformed TSUN tail, then I can dualize the bifundamental between the two different ranks, okay, like this, okay? So another important property of this deformed S-duality world is something similar to Hanani-Witten transition in type 2B string. So you remember when you realize this 3D mirror symmetry in terms of branes, you should use this Hanani-Witten transition, right? And of course, since we construct the 3D mirror from the field theory perspective, we need something similar to that. And it turns out this deformed TSUN tail together with another copy satisfy exactly the same relation as in the Hanani-Witten move in the brane picture. So we can swap the bifundamental field and this one. Then the rank in between changes like this, which is exactly the same as the condition from the Hanani-Witten move. The thing is that, so then what is the field theory interpretation of this relation? So once you expand this theory in terms of the original quiver, then you can really check that this is nothing but just the Higgs mechanism. Once you construct this quiver theory and check whether there is a Arch flow and what the result of Higgs mechanism, Arch flow, then we find that they flow to the same theory, which is just a Higgs mechanism triggered by the this property. Because there is a BAB on every point on the moduli space, there should be a Higgs mechanism. Okay, so far I have shown you just the ingredient I need. And now let's jump into the example. So I'm going to consider the U2 SQCD with the 4 flavors whose mirror symmetry is well understood. Okay, but now I just explain this mirror from our algorithm perspective. So as a first step, I first decompose this theory into the building blocks like this. So we have a 4 fundamental and 2 bifundamental, trivial bifundamental in this case, because you can see that one side we have a 0 rank. But I just introduced this component to correctly incorporate the FI parameter of the theory. So this is the FI parameter of the gauge node. And then I can dualize its field using the relation I show you. So this bifundamental becomes this fundamental. And this fundamental field becomes bifundamental field sandwiched between the 2 TSUN. But you remember the adjacent TSUN just collapse. So any TSUN, colliding TSUN in between will disappear, and we are left with the 4 bifundamental field here. And we also dualize this piece like this. And then you can recall, so look at this part. So this is exactly the same as this one, which means we can apply this relation, the Hanani-Witten-like relation. So I apply this relation to this part, then what I get, okay, this part, then what I get, this one, okay? And then we can also recognize another part, another component, to which we can again apply this Hanani-Witten move. So I apply the second Hanani-Witten move to get this, okay? And then we just have a bunch of this TSUN tail, okay? So actually, I forgot to mention that. So I'm going to call each TSUN tail as an S-duality wall. So the original name is related to the fact that this TSUN theory can be realized as some domain wall for the n equal to 4 maximal super Young mills. But at the moment, you can just regard it as a name. So I'm going to call this as a S-duality wall, and the 2 S-duality wall combined as an identity wall, whose meaning is clear, because as I mentioned, the rollover identity wall just triggers a Higgs mechanism, which breaks the 2 global symmetry into the diagonal one, okay? So in this case, we also expect that the role of these colliding identity walls are just identifying those 2 global gauge symmetries, U2 global gauge symmetries. So we obtain this theory, which is exactly the known mirror symmetry of the U2 with the 4 flavors. The thing is that in this derivation, I never refer to the string theory setup. I just use the field theory duality to derive this relation. And as I mentioned, these fundamental building blocks are also derived from just the most fundamental thing, the R-only duality. So if you assume the R-only duality, this should hold, okay? Okay, so yeah, it is the field theoretic algorithm constructing 3D mirror pairs. And the core idea is that, as I mentioned, we dualize its field rather than the entire theory. And due to this fact, we can easily generalize this story to some more complicated quiver gauge theory, like a linear quiver or circular quivers, because they also consist of the same type of field. either either fundamental or bifundamental field. And moreover, we don't need to stick to the good theory case. Okay, so we can go beyond the good theory, which is bad theory, which I will explain. But before moving on, there is another important remark. Yeah, they are all derived from the same building blocks, regardless of whether it is a QCD or some linear quiver or circular quiver. And these building blocks are, as I mentioned, they descend from the R-only duality. So there is a kind of chain of derivation. Starting from the R-only duality, we can derive the building blocks of 3D mirror symmetry. And then we can cook up, using these building blocks, we can cook up some complicated mirror examples. It means some mathematical identity corresponding to this duality for any supersymmetric partition function is automatically proven, assuming that of R-only duality is true. Okay? So indeed, for example, the identity for the R-only duality is proven for squashed 3-sphere partition function, and it is also proven for the superconformal index. But here I just put almost because actually in order to use this identity, we need a slight generalization allowing the background flux. But anyway, so the R-only duality is the identity for R-only duality is also proven for the S3 partition function and superconformal index. So basically, the relation I show you guarantee that the supersymmetric partition function identities are automatically hold. Okay, so now let's move on to bad theory, as I promised. So what is bad theory? Let me first explain what it is. So 3D n equal to 4 gauge theory admit chiral monopole operators whose fab parameterize the Coulomb branch of the moduli space. For UN gauge theory, we can determine the naive conformal dimension or R charge of those bare monopole operators by using this formula. And as you can see, if we have a small number of flavors for given gauge rank, the dimension of the monopole operator becomes negative or smaller than 1/2. Okay? And in this case, we know the unitarity is violated, and we call such a case as ugly or bad theory. So it doesn't mean that theory is ill-defined. We just know that, okay, there should be an emergent symmetry which correct this UVR symmetry such that the correct R symmetry will be larger than this 1/2 or larger than or equal to 1/2 to be unitary theory. Okay? And as I mentioned in the introduction, so if I try to compute the partition function using this UV data, either matrix integrals or some flux summation for superconformal index, for example, the partition functions are not convergent. Okay? Then why this mirror dualization algorithm helps to resolve this issue? It turns out the mirror dualization algorithm naturally organizes the partition function of a bad theory into the sum of those of good theories multiplied by delta distribution. In other words, somehow you can systematically extract this divergent piece out of the divergent partition function of bad theory. Okay, so now it is more tractable, more easy to understand. And in that sense, I would say the partition function of a bad theory is not a function, but it's a distribution. Okay? Yes, please. That's a very good question. So here distribution means a Dirac distribution. So it means that Dirac distribution in the symmetry fugacities. Okay, it means the symmetry must be broken at the point. So it's basically spontaneous symmetry breaking. Okay. Any question? Any other question? Yes, please. If you turn on some non-zero back. So usually if you compute the partition function or superconformal index, for example, you obtain the observable for the fixed point, right, which is interacting CFT, right? So unless you turn on some web of operators by hand, there is no symmetry breaking. Okay. Of course, if you turn on the web by hand, then there should be some symmetry breaking, but it is not automatically encoded in the partition function you compute. But our result tells us that, okay, you cannot avoid this symmetry breaking. So whatever point you flow to, there should be a spontaneous breaking due to the decoupled monopole, which has a non-zero web. Okay.
So this modular space, does it not have a safety point?
I mean, it can have a safety point, but it should be multiplied by some decoupled field. So yeah. Not yes. 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 Yeah, good point. Yes. Okay. So let's move on to the example, the bad example. So previously I considered U2 with the 4 flavors. Now I increase the rank by 1. So U3 with the 4 flavors. And you can easily check that. So this violates the positivity condition for this conformal dimension. Okay, so I do exactly the same procedure. So just decompose the theory into the blocks and dualize each component. So this becomes this becomes this, and this becomes this. And then I apply the Hanani-Witten-like move to this component. So this becomes this. So we have this one. The thing is that, unlike the previous case, where we just have a colliding original identity walls, now we have colliding deformed identity walls. Okay, so previously we just have 2, 2, 2, 2. So it is just identity, standard identity walls colliding. But now we have a deformed identity walls colliding with each other. So it means we cannot just remove this part. So previously we can just drop the identity wall part. On the other hand, this part now non-trivial for bad theory, and we cannot just drop this part. So what does it mean? So the first lesson we learn is that if I apply the mirror symmetry to bad theory, the dual theory is not actually Lagrangian ones. But I'm not saying it's not completely non-Lagrangian. It's not complete, sorry. It's not completely non-Lagrangian. Yeah. So I would say it's a semi-Lagrangian dual. What do I mean by that? So I call this theory as a semi-Lagrangian dual because this is a theory obtained by gauging emergent IR symmetry of Lagrangian theories. So if you look at this part, so it looks like this. I obtained this theory by gauging 2 copies of this component. Okay? But the thing is that the symmetry I gauge here is actually the emergent symmetry of this Lagrangian theory. So ingredients are all Lagrangian, but I just gauged the emergent symmetry of the Lagrangian theory. So I would call this as a semi-Lagrangian dual theory. That's the first lesson we learned. So the mirror symmetry of bad theory is semi-Lagrangian in this sense. The second lesson is that we don't need to stop here. So we can further follow the algebra flow into the deep IR and examine what happens. So we remember that the role of this identity wall is just triggering some symmetry breaking. But it is more complicated for deformed S-duality wall. The reason is the following. So on either side, so here or here, originally we have U3 symmetries, okay? But now we only gauge the part of it. So we only gauge the U2 out of U3, and the other U1 remains as a flavor symmetry. And then if we follow the algebra flow triggered by this identity wall, because you remember, this identity wall has a smooth moduli space with non-zero web at every point of the moduli space. And depending on which point we are sitting at, there are two types of symmetric breaking patterns. So firstly, if we identify so this Z1, Z2, and Y1 are symmetry variables. So those are two U2, and this is for this U1, global symmetry. And if we identify the symmetry in this way, the U2 remains unbroken, but there should be a spontaneous symmetry breaking between these two U1 global symmetry, okay, like this. On the other hand, if we identify the symmetries in this way, so you can see that, so this one is identified with this one, but if we identify Z2 with Y2, this basically means the Higgs mechanism. So originally we have a U2 with the two U1 global symmetries, but due to the Higgs mechanism, this U2 is broken down to U1. But this global symmetry remains unbroken, okay? So we have two phases of this theory in the IR. So one phase is this theory with a broken flavor symmetry. So we only have a U1, single U1 symmetry. And the other phase is governed by this theory with unbroken flavor symmetry. So we have original bad theory and semi-Lagrangian dual theory, which has two phases in the deep IR. So if I represent it pictorially, it looks like this. So we have an original theory, which is due to this semi-Lagrangian, and it has two different phases depending on which point you are sitting at on the moduli space. Okay. The thing is that one theory, there should be a spontaneous symmetry breaking of the flavor symmetry, and the other point, there is no such thing. Okay. Any question? Okay. Yes, please. Yes. So this relation means, so if you compute the partition function of this theory, you can decompose the contribution into two pieces like this, one of which is accompanied by this delta distribution. Okay. And I'm going to call these multiple frames as magnetic dual frames. Okay. So in general, a bad theory has a semi-Lagrangian mirror dual, which further flows to the multiple magnetic dual frames in the deep IR. But the thing is that each magnetic dual frame is a good theory. So you can check, yeah, this is a good theory, this is a good theory. So they have a well-known mirror duality pair. So it means I can dualize them back into the electric side, and then we can represent the original theory in terms of two electric theory, which look like this. They are just obtained by dualizing each magnetic dual. So once I dualize this, it becomes this. And once I dualize this, it becomes this. And what is the interpretation of this electric dualization? It is nothing but just the result of monopole Higgsing, so as I mentioned. So this delta indicate the symmetry breaking due to the web of some decoupled monopole. And then the gauge group is, of course, Higgs due to the web of monopole operator, and it becomes U2 with the fourth flavor. If there is no delta, the interpretation is more like a Seiberg duality. So you remember, so if you naively apply the Seiberg duality, there is a fourth flavor and gauge rank is 3. So you expect that the dual theory might be described by U1 with the four flavors. So it means that, okay, this bad theory is two components. So one like a Seiberg dual, and the other like just a monopole Higgsing. Okay. But this is just a specific case for this choice of U3. And in general, if you consider U1 SQCD with F flavors, it is decomposed into the set of theories, rank R SQCD with F flavors, where R runs from the integer part of this F over 2 to the F minus n. And this is exactly this consistent with the result by Arthur and Cremonesi, who examined the moduli space of this bad n equal to 4 series. Good. So I have explained what this mirror dualization algorithm and how can apply it to the bad theory. And using this, I'm going to attack these circular quivers. Any questions so far? Yeah. If not. Okay. So we can apply exactly the same mechanism, same steps to dualize the circular quiver, but we need a couple of more ingredients, because if you consider the circular quiver like this, actually we can introduce one more symmetry, the baryonic symmetry, under which the loop-like operators are charged. So in order to introduce this baryonic symmetry, we need to insert the shifted delta. Okay, so we just insert, so yeah, this baryonic symmetry, mass parameter for baryonic symmetry can be realized once you insert this delta in between. And this can be realized in terms of our building blocks as like this. And you can check the shift of mass parameter on one side is the equivalent to the extra Fy coupling in the middle node. Okay, this is good because we know that the mirror dual of this baryonic symmetry is the topological symmetry, and we can explicitly see that. So once I dualize this again, so I just attach the extra S duality wall on both sides, then they just disappear. I left with this one with a topological symmetry, which is dual to the baryonic symmetry. Okay, so everything is consistent. So now I'd like to apply this to the good circular example. So I'm going to consider the self-dual M2 brane theory, one of the self-dual M2 brane theories. So the theory I'm considering is the circular quiver of L gauge node with a constant rank n. Okay, and I attach a single flavor at each gauge node like this. And it is known that this is the low energy effective theory of n M2 branes probing square of C2 mod GL. Okay, and if I take L equal to 1, it becomes just a ADHN quiver I mentioned in intro, which flows to the 3D n equal to 8 superconformal field theory. So how to dualize this? So as in the SQCD case, I decompose all the components like this. So as I mentioned, this baryonic symmetry can be realized as an insertion of the shifted delta. And I also insert this extra Fy parameter to one of the gauge nodes. And then we have a sequence of fundamental field, bifundamental field, and so on. Okay, so I just decompose the theory into this, and then dualize each component. Okay. So this is n equal to 4 theory. So the superpotential is standard. So we don't turn on any extra superpotential by hand. So once we dualize, this becomes just a topological symmetry without the S duality wall. And this topological Fy parameter becomes the baryonic symmetry, shifted delta, like this one and this one. And as before, I can dualize this fundamental field into the bifundamental one, and this bifundamental field into the fundamental one. So everything is swapped. So now I have a bifundamental, fundamental, bifundamental, and so on. And once I combine them, I get exactly the same form of theory, but now the topological symmetry and topological symmetries and flavor symmetries are swapped. Okay, and this is the expected result, which is the self-mirror symmetry exchanging the Coulomb and Higgs branch of the theory. Okay, so of course you can obtain this result using the type 2B brane, but this is purely field theory derivation. Yes, please. Yes.
You mentioned, okay, It's related to, okay, so this is topics called
Yeah.
and that is the response to these two the order of before the actually the same.
Yeah, exactly. Excellent. You mean yeah, different? Yes, of course. Yes. Yeah, this is just a simplest example in that sense. So of course there is a theory with a different order of this quotient. Yeah. Right. Yeah. Okay. So this is an example of good circular quivers, and then let's move on to the bad case. As I briefly mentioned, for bad circular quivers, we have two types of badness: local badness and global badness. Firstly, for local badness, that is due to again the violation of the unitarity due to the monopole operator charged on the specific gauge node. The same unitarity bound for the conformal dimensional monopole operators still hold. So the R charge or conformal dimension is determined by the same formula I show you, where the number of flavors now I use is the effective one. So the number of flavors attached to that node plus the rank of adjacent gauge node. And if this relation holds, we say there is a local badness of the quiver, and we will encounter the decoupling monopole operator, which is charged under the specific gauge node. On the other hand, there are also a slightly different types of monopole operators which are charged under the diagonal U1, which means it has a flux for all the gauge nodes, okay? And their R charges are not governed by this local formula, but the thing is that there are this diagonal monopole operator whose conformal dimension again becomes less than 1/2 and violate the unitarity bound. And we call such a case as globally ugly or globally bad, depending on whether it has exactly the R charge 1/2 or less than 1/2, okay? Okay, so let me show you an example. So the first example is local badness, okay? So for this local bad circular quiver, we can again apply this procedure of decompose and dualize and combine them back. But instead of doing that, let me just do the electric dualization, which I learned from the SQCD example. So I mentioned that, so we can either do the magnetic dualization or electric dualization. And in this case, electric dualization is much more convenient. So I directly apply this electric dualization, which just reduce the UN gauge group, bad UN gauge group into the set of reduced theory with a reduced ranks like this. So let me show you an example. So if I consider this theory, so this is a circular quiver, and you can check that those two are good, but this one is bad, okay? Then it means this bad theory flows to have two different phases, okay? So one is governed by the rank of this, and the other is governed by the rank of this, okay? So in this case, the resulting theory is good, so it stops there. But in this case, we encounter a node which is ugly, which means that the monopole operator charged under this node has exactly the conformal dimension 1/2, and it should decouple. And then we can dualize this further to this using the same relation, and the resulting theory looks like this, okay? So yeah, so starting with this bad circular quiver, we find two different phases in the IR, and one is this associated, accompanied by some delta. Here, for simplicity, I just do not explicitly indicate the precise FI parameter, but basically the idea is the same. So in this phase, you will encounter some symmetry breaking of the flavor symmetry, in this case, topological symmetry. And in this case, you don't.
Here from obifolding or modified motivated by came up with an example.
I don't see the direct connection. I mean, I cannot say whenever you have a good overfold, you will encounter bad theory. Because it just depends on the number of flavors and ranks. So yeah, it can appear in a, yeah. Yeah, generically you have a bad case, yeah. So this is a local bad example. But the question, you might wonder, so okay, so in this case, for each resulting theory, you only have one chain of dualization. So in this case, you just dualize this, and in this case, you dualize this and this to obtain this. But in general, there might be multiple ways to obtain the same theory at the end. And you might wonder whether the result is independent of the order of dualization. We expect so because otherwise it depends on the order of dualization and it doesn't quite consistent with our physical intuition, right? And we don't have a general proof, but we checked using computer millions of examples, and this is the case. It is independent of the order of dualization. The list of resulting theory is independent order of dualization, given that the axial symmetry is not broken, which is somewhat natural because we expect that n equals to 4 symmetry is still preserved in the IR. So this shouldn't be broken explicitly. And another condition is that the resulting singlet. So whenever we dualize this, we have some decoupled monopoles, which are realized as a singlet, gauge singlet, of course. And they should not have vanishing conformal dimension when the delta conditions are imposed. I mean, it sounds very technical. It is not very natural from the physics point of view, but we have checked that whenever this happens, if there is a singlet with a vanishing conformal dimension, you can actually carefully check. This is not the independent frames, but it is just some limit of other resulting frames. So we shouldn't count them independently. So as long as those two conditions are hold, the resulting dual theories are independent of order of dualization, which is one of the consistency checks. Oops. Okay. Any question? Yes, please. Which one? This one or? Maybe you're right. Maybe you're right. Then you can dualize it once more. You can keep doing that. Yeah. Anyway, so the point is that in this example, there is one way to follow the dualization for this path, and probably at the end you may get some West-Gemino theory without gauge group. It is completely fine. Yeah. But anyway, it is good. Yeah. At the end. Yeah. Thank you for pointing this out. Yeah. And now let's move on to the global ugly and global bad theory. Okay. So the next example is this one. So unlike the previous example, I removed all the flavors except one. And this theory describes the M2 brane probing C to mod GL times C2, which is one of the examples Nagu considering. Right? And this is a mirror dual to the ADH and Quiver with the L flavors. And you can check, in this case, there is no local gauge node violating the local goodness of the node. Okay? So there is no decoupling monopole operator if it is only charged on the single gauge node. On the other hand, there are a pair of diagonal monopole operators whose conformal dimension is 1/2. So it's ugly. So which looks like this. So this M is charged on the every gauge node with a unit flux. Okay, and it's and also there is a negative flux counterpart. But we can still apply this mirror dualization algorithm. So I just decompose this theory into the component and dualize each one to obtain this. So for example, so this one fundamental flavor becomes bifundamental. And those bifundamental becomes fundamental flavors. And if I combine them, then I just get the UN, single UN theory, and this becomes just adjoint field, and all the other fundamental fields combine to form SUL gauge global symmetry. Then you can check those decoupled diagonal monopole operators are mapped under this mirror symmetry to the trace part of this adjoint hyper, because it exactly has one conformal dimension 1/2. So everything is consistent. Okay. The thing is that we can apply the same procedure for this global ugly theory, and yeah, everything is consistent. Now, the last example is the global bad circular quiver, which is the most interesting thing. Now I remove the flavor completely. So we only have a circular quiver without flavors. And if we take the L equal to 1, if we just consider single gauge node, it is just a S super Yang-Mills with a one adjoint hyper, which is nothing but N equal to A super Yang-Mills we considered in the introduction. And again, you can check there is no gauge node violating the local goodness. Nevertheless, there are a set of diagonal monopoles of 0 conformal dimensions. So you can turn on uniflux for each gauge node, or twice of the uniflux like this. It's not +2, it's +1, and so on. And all those monopole operators have 0 conformal dimension naively. Okay. Then what's the mirror dual of this theory? So again, we just decompose this theory into the block. But in this case, it's very simple because we only have a single adjoint hyper. It is nothing but the bifundamental. And once I dualize this and glue back, then as I show you, this one is dual to the fundamental hyper sandwiched between two SUN. And I need to glue those two UN back. So once I combine them, then I get this one, which is, yeah, the semi-Lagrangian mirror dual. So claim is that the mirror symmetry of this 3D n equal to A super Yang-Mills is semi-Lagrangian ones looking like this. Okay? And as I mentioned, this is not the end of the story. We can also further follow the RG flows. The thing is that since now we identify the gauge group with itself, so the pattern is slightly different. So I need to identify the set of gauge variables, G1 to the Gn, with shifted, the same set of gauge variables, but shifted by E, the topological symmetry. Yeah. And yeah, so for concreteness, let me consider the n equal to 3 case, which looks like this. And there are 3 patterns. We just simply identify in this way. In this case, so you can see that if I identify in this way, we get the condition that the E should be 0, right? So we have a delta, 3 delta of E. And since we identify G1 with the G1, G2 with the G1, and so on, so in the end, we just get 3 copies of U1 QED. What about the second case? So if I identify this way, so so from this, we have a delta of E. From this, we have a delta of 2 times E. And then this node and this node should be identified because we identify G2 with the G3. Okay, so the resulting theory looks like this. And lastly, if I do this identification, the resulting theory is just a single QED with multiple flavors. Okay. So let me speed up. So they are magnetic dual frames. And let's go back to the electric frames by dualizing each one. Then the resulting theory looks like this. It is quite surprising. Although it is not obvious, it is surprising because if you consider classical picture, the U3 gauge node can be broken on the Coulomb branch into the bunch of U1 like this, right? But if some of the cartons of this adjoint field happen to be the same, then the non-abelian symmetry is restored. So you have a U, at some point on the moduli space, you would get U2 times U1 or even U3 at the origin, right? So that's our classical picture. But our computation tells us that there is no such non-abelian restoration. Every point, the IS theory governing the dynamics is just a 3U1 or this circular U1, circular quiver with a 2U1 node, or this one, which is different from our classical perspective. And this is general situation, not just for n equal to 4 super Yang-Mills. I can consider some longer quiver, usually with a 4 node. I can do the same steps like this. And at the end, what I get is this picture. So in the IR, depending on the modular space you are sitting on, so this is the same as a typical Coulomb branch, U3. Each U3 just broken into the bunch of U1, right? On the other hand, you don't get the U2 theory, U2 circular quiver. Instead, you have enlarged circular quiver with the abelian gauge node, okay? And also something like this. So in general, the IR dynamics of this bad circular quiver, globally bad circular quiver, is described by the enlarged abelian circular quiver rather than some non-abelian theory. Okay, and you can check this non-trivial theory appears when the BEV of monopole operators with non-uniflux is turned on. Okay, so that's why it is not consistent with a classical picture, because classically these monopole operator with non-uniflux is not independent ones, so they don't appear in the classical analysis. But if you compute the supersymmetric partition function like this, it should incorporate all the quantum effect, and it turns out there are independent monopole operators with the unifluxes, and they lead to this abelian structure in the IR. Okay, and for general n, so from this you can easily guess how to generalize to arbitrary n and L, and it turns out this classification, I mean, so in this case we have 3 cases, but in general, the possible cases are classified by the Young diagram. Okay, that's another lesson. The true question is, of course, how we can make a contact with n equal to a superconformal field theory. Unfortunately, the answer is not clear at the moment, because so we can write down, for example, partition function in terms of those of good theories like this, but in order to compare it with n equal to a superconformal field theory, we need to know how to refine the partition function, okay, which is not clear at the moment. But the thing is that anyway, using this UV, putative UV data, we can write down the partition function or index, whatever, for this bad theory, which shows this structure. One quick check we can do, however, is the following. So we cannot make the precise comparison with, for example, other n equal to a superconformal theory description. We can check how the free energy of this decomposition scales like, okay? So we found that it's because we know in the large limit, it should correspond to n equal to s CFT, which has n to the 3½ degrees of freedom. You can ask whether that is the same here. And yes, so for each frame, you just have n. So usually case, you have 3 U1 or sorry, here. So you always have rank 3 for each frame. So at first it looks we lose degrees of freedom, but it turns out this Young diagram summation provides exactly the e to the square root of n, and once combined, you recover this n to the 3½ at the end. So it is consistent with the holography. Okay, so yes, please.
Here, e to the n to the half times e to the n is e to the n plus.
Oh, sorry. Yeah, maybe I did something wrong here. Yeah, but yeah, we can discuss later. Yeah, yes. Thank you for pointing that out. Okay, so summary. So time's up. So 3D quiver gauge theories include many interesting models, such as the low energy theory of empty brains, but large class of such examples are bad and ugly. And our mirror dualization algorithm provides a systematic way of rewriting the partition function of bad theory into the sum of good theories multiplied by delta distribution, which is more tractable. And a new pattern of monochroming is observed from the partition function of bad circular cube as I just explained. And the remaining question is, at the moment, it is not clear how to compare this n equal to the partition function we obtained with other description like ABJM or ADHM Quiver description with this n equal to A superconformal field theory. And although today I only focus on the bad case, actually there are many possible generalizations, like a generalization to SL2G, not just the mirror symmetry, generalization to lower supersymmetry, and even for 4D, and so on. So this is a very interesting business, I think. So yeah, for example, you can find the same type of building blocks for SL2G. And the example I show you, the self-mirror dualization, self-mirror M2 brane example, can be extended to the SL2G triality. This is just a generalization of ABJM. And also there's an n equal 2 version of this. It is interesting. It was, so if you consider the n equal to 2 SUN QCD, it is due to this abelian planar theory. And yeah, so there are many interesting directions. And the bottom line is the mirror dualization algorithm is a new window into the dynamics of 3D gauge theories and mirror symmetry. And yeah, thank you for your attention.
Other questions or comments? No. Yeah, I think we had a lot of questions during the talk, and so let's thank Chiung again, and yeah. So we're gonna resume at 3:30.